This question was asked in the GATE Physics paper 2021. This is a multiple select question, that is MSQ, having 1 mark. The topic of the question is solid state physics. Specifically, this question was asked from the chapter reciprocal lattice. The question is, a two-dimensional square lattice has lattice constant small a. K represents the wave vector in reciprocal space. The coordinates kx, ky of reciprocal space where band gap or band gaps can occur, those are: option A is at 0, 0, that is at origin; option B plus minus pi by a, plus minus pi by a; option C plus minus pi by a, plus minus pi by 1.3a; and the last option, option D, plus minus pi by 3a, plus minus pi by e. So as this is a MSQ type question, so it is possible to have multiple options correct for this question. So let us see how to solve this problem. Before going to the main part of the solution, let us discuss very briefly about the Brillouin zone and how can we construct the Brillouin zone for a 2D square lattice having lattice constant small a. So what is Brillouin zone? Brillouin zone is the locus of all those k values or k points in the reciprocal space or k space of a crystal structure which are Bragg's reflected. So you can see here a schematic which basically describing the first and second Brillouin zone of a 2D square lattice having lattice constant small a. So let us understand how can we describe the first and second Brillouin zone for this from this schematic. So you can see here a square region which is shaded by the horizontal lines, and origin is at the middle of the square. So this square region is basically bounded by 4 straight lines. Those are kx equals to minus pi by a, kx equals to pi by a, ky equals to pi by a, and ky equals to minus pi by a. So this square region is the first Brillouin zone for the 2D square lattice in the K space, that is kx, ky plane. And these 4 sides, which are basically the 4 straight lines, these are the first Brillouin zone boundaries. So this is how we can describe the first Brillouin zone boundary for a 2D square lattice. Now what about the second Brillouin zone? So to construct the second Brillouin zone, basically we need these 4 straight lines kx minus ky equals to minus 2 pi by a, kx minus ky equals to 2 pi by a, kx plus ky equals to minus 2 pi by a, and kx plus ky equals to 2 pi by a. So these 4 lines, straight lines, will basically construct the second Brillouin zone for the 2D square lattice. So the area enclosed by these 4 lines, excluding this first Brillouin zone area, will give the second Brillouin zone. So basically these 4 region shaded with vertical lines will basically give the second Brillouin zone of the 2D square lattice, and the boundary lines are the second Brillouin zone boundaries. Now let us see how can we basically construct these Brillouin zone and Brillouin zone boundaries from the vector form of the Bragg's law. So let us see. In the previous slide, we have already seen the first and second Brillouin zone for the 2D square lattice having lattice constant small e. Now we'll understand how can we construct the Brillouin zones and Brillouin zone boundaries from the mathematical equation. For this, we need primitive translation vectors for the 2D square lattice. Those are a vector equals to a I cap, that is along x cap direction, and b vector equals to a j cap along y cap direction. The corresponding translation vectors in the reciprocal space, that is in the K space, will be a star vector equals to 2 pi by a along I cap direction, and b star vector equals to 2 pi by a along j cap direction. So by knowing these a star and b star vectors in the K space, we can construct the reciprocal lattice vector, that is g vector equals to 2 pi by a times h I cap plus k j cap, where h and k are the integers. And the wave vector in the k space, that is k vector, is basically kx I cap plus ky j cap. So the vector form of the Bragg's law is given by this equation. This equation is 2 times k vector dot product with g vector plus g square equals to 0. From the earlier slides, we have already seen this k vector is the wave vector in the kx ky plane. So this k vector will be kx I cap plus ky j cap. And g vector basically denotes the reciprocal lattice vector for the crystal structure, two-dimensional square lattice. So this g vector for the two-dimensional square lattice will be 2 pi by a times h I cap plus k j cap. Now we'll put all the expressions for the k vector and g vector in this equation. Then we'll get 4 pi by a times kx I cap plus ky j cap dot product with h I cap plus k j cap plus 4 pi square by a square times h square plus k square equals to 0. So this second term is coming for the g square term here, and this 2 times k dot g vector is giving this first term in this equation. Now we'll perform the dot product here. It will give the kx I cap dot product with h I cap will give the hkx, but this kx I cap dot product with kj cap here will give the 0 because I and j are the unit vectors orthogonal to each other. Similarly, qij cap dot product with h I cap will give 0, but the qij cap dot product with kj cap will give kky. So after some rearrangements, we'll get this equation hkx plus kky equals to minus pi by a times a square plus k square. Here h and k are the integers. So what does this equation tells us? So this equation basically telling us about the location or locus of the k points which are Bragg reflected. Now h and k are the integers. So first we'll put h equals to plus minus 1 and k equals to 0. So this will basically lead to kx equals to plus minus pi by a and ky can be any arbitrary value. Similarly, we can put h equals to 0 here and k equals to plus minus 1. This will basically lead to ky equals to plus minus a and kx can be any arbitrary value. So from this combined of these conditions, we can get kx equals to plus minus pi by a and ky equals to plus minus pi by a. So these are basically constructing the boundaries for the first Brillouin zones. So these 4 lines will give the first Brillouin zone boundaries here. That we have already seen in the first schematic diagram. So till now we have already seen how can we construct the first Brillouin zone boundaries for the two-dimensional square lattice from the vector form of the Bragg's law. And those 4 lines are kx equals to plus minus pi by a and ky equals to plus minus pi by a. So these 4 lines are the boundaries for the first Brillouin zone that we have constructed mathematically already. Now we'll consider the second possible integer values for the h and k. So those are h equals to plus minus 1 and k equals to plus minus 1. So if we put this h and k value in the equation of the locus of all k points, those are Bragg's reflected, then this will get another 4 lines which will basically give the boundaries for the second Brillouin zone in the 2D square lattice. So then we will get these 4 lines kx minus ky equals to minus 2 pi by a, kx minus ky equals to 2 pi by a, kx plus ky equals to minus 2 pi by a and kx plus ky equals to 2 pi by a. These four lines will basically construct the second Brillouin zone boundaries in the kx and ky plane. So now we have the idea how can we construct the Brillouin zones for the 2D square lattice, and how does it look for the first Brillouin zone boundary and second Brillouin zone boundary. Now, whenever an electron strikes the Brillouin zone boundaries, its group velocity, which is given by Vg equals to 1 by h car del E del k, where E is the energy and k is the wave vector, that becomes 0 as at the Brillouin zone boundaries. What does it mean? It leads to basically the generation of energy band gap or energy gap at the Brillouin zone boundaries. Hence, all points lying on Brillouin zone boundaries will give rise to energy band gap in the crystal structure. Now, all the k points of first Brillouin zone boundary lies on the four lines. Those are kx equals to plus minus pi by a. These two lines are shown here, kx equals to minus pi by a here and kx equals to pi by a, and ky equals to plus minus pi by a. Those two lines are here, ky equals to pi by a and ky equals to minus pi by a. So these four lines will basically construct the boundary of the first Brillouin zone, and at all the points on this boundary we'll get the energy band gap. Now there are 4 points given in the options. First option was 0, 0, that is the origin. So the origin is not lying on the boundary. So it is not possible to have the energy band gap at the origin. So this option can be eliminated. Now for the other 3 options, so we will just discuss one by one. First, second option was plus minus pi by a, comma plus minus pi by a. So these are basically 4 points. These 4 points are here at the corner of the square. So these are lying on the boundary of the first Brillouin zone. So this is the possible answer 1. So then the third option, plus minus pi by a, comma plus minus pi by 1.3a, these points are lying somewhere like here, here, or here and here. So these 4 points will lie on the boundaries. So this is also possible answer. And for the last option D, plus minus pi by 3a, comma plus minus pi by a, these 4 points will basically lie somewhere like here, here, or here, or here. So these 4 points will lie on the boundary of the first Brillouin zone. So this is also the possible answer. So effectively we are getting option B, C and D are correct for this question. We have already discussed in the earlier slides about the Brillouin zone. Then how to construct the Brillouin zone for a two-dimensional square lattice that has lattice constant small a. Then we have discussed how the energy gap or band gap can arise at the zone boundary, that is at the boundary of first Brillouin zone, second Brillouin zone, or so on. And after that we solved this problem and we found that the option B, C and D, that is at plus minus pi by a, comma plus minus pi by a, plus minus pi by a, comma plus minus pi by 1.3a, and plus minus pi by 3a, comma plus minus pi by a. So these 3 options B, C and D, at this point in K space the band gaps can occur. So these 3 options are the correct answer for this question.